Good morning, everyone. Welcome back for lecture 13, and this will be the continuation of the addition reactions to alkenes. So, as you probably already heard from the exam review or exam solutions video, I have decided to give everyone a 16-point curve on this particular exam. Um, uh, the details, of course, will be in the exam solutions video if you haven't already seen it yet. Just a reminder, though, we do have another exam by the end of the week. We're going through this pretty fast. Tomorrow we'll be doing alkynes, and also Thursday. That's that's sort of a short chapter. So, luckily for both of us, for all of us, that exam 4 won't have as much information on it as previous exams. But then the week after will be a super busy week because you have 3 chapters left to go through. Your final exam of the entire class is on Thursday, and so is your um, your lab final is also on Thursday too. So don't forget any of that stuff. Um, and then as for today, though, don't forget you do have a lab assigned today on IR spectroscopy. There will be a pre-lab video for you to watch for that. Pre-lab lecture video that I'll post for you to watch for that, and then you can watch the stuff in LabFlow and do that experiment. With that being said, let's go ahead and get started then. Okay, let me move the view over. There we go. Addition reactions of alkenes. Kant. Again, Kant. Okay. So, just to continue on with what we were talking about yesterday, we can talk now about syn addition, right, onto alkenes. And one very useful reaction is the hydrogenation reaction, okay? And it's exactly what it sounds like. You're adding hydrogens, specifically a H2, right, a hydrogen molecule across double bonds, right? And luckily for us, this is stereospecific, but it only does syn addition. So you've heard of hydrogenation before, mostly in fats. When you're talking about, for example, fatty acids and butter or margarine and stuff like that. And what you'll see is a lot of times they'll try to take liquid fats, right, that are like oils, like maybe olive oil or vegetable oil or something like that. Those have double bonds in them, right? And we'll get way more detail about that later on in life. But they have double bonds in them, so they're actually not what we call saturated. They're called unsaturated fats. And since they're unsaturated fats, they tend to be liquid at room temperature, right? They tend to be liquid at room temperature. And like I said, that's stuff like canola oil, vegetable oil, peanut oil, olive oil, all those things that are oils. They have double bonds in their molecule, in their fatty acid molecule, and it makes them liquid at room temperature. Well, in an attempt to make butter more healthy, because unsaturated fats are far more healthier for you than saturated fats are, unsaturated fats actually play a role in high density lipoprotein, which actually helps in reducing heart disease and such. Um, but everybody likes the solid fats, like the butters and stuff like that, because you can't spread oil on bread and make nice, buttery toast on it, right? Or and stuff like that. So, and then also the other reason why too, that not just because it doesn't spread like oil doesn't spread like butter does. Butter sometimes when it gets too cold, it's too hard to spread, and so they want to make butter a little bit more soft, so it's easier to spread. And so they come up with things like margarine or butter substitutes. And one of the ways they do that is by taking vegetable oil, right? And what they're doing is they're partially hydrogenating it. And so that literally what they're doing is they're adding hydrogens using hydrogenation action, right? Hydrogenation, Let's try that one more time. Hydrogenation reactions, right? To turn the oils that have double bonds in it to make them saturated, right? To make them saturated. So once they get saturated, you get this mixture of saturated fats and unsaturated fats together, and the unsaturated fat portion, which is the oils that got partially, or the oils that got hydrogenated, right? mixed together with the other fats, and it makes it a little bit more spreadable and stuff. So the only problem with this is that you don't come up with 100% hydrogenation. In fact, if you look on the back of like things like country crock or other butter substitutes like spreads, right? You'll see in the ingredients that it's labeled partially hydrogenated. And so the reason why is because you can never get like 100% hydrogenation, and when that happens, you'll get this thing called trans fatty acids. Okay, so remember that double bonds happen right in fatty acids, and that makes them liquid oils, right? And all those are generally double bonds that are in the cis configuration, which are perfectly fine. They in fact they help you by being a huge component of high density lipoprotein, as opposed to low density lipoprotein that really causes plaque in your arteries, right? And so it's fine to have double bonds because double bonds are good in oil, except for when they're trans double bonds. And so those are called trans fats. And trans fats have been shown to actually be very harmful as far as heart disease goes and cardiovascular function goes. And so that's why I tend to stay away from things like, partially hydrogenated, fake butter. If you're going to use butter, you might as well use real butter. And if you're going to use oil, you might as well use real oil and not use some kind of weird mixture or substitute that has trans fats in it, because it actually is very damaging to your cardiovascular system, right? Because you don't want to trans fatty acids; those are bad. But that's what that comes from, right? So to do a hydrogenation reaction across a double bond, as you see here, right? Literally all it needs is hydrogen gas and a catalyst. In this case, the catalyst is platinum, right? When this reaction occurs, you get two chiral centers, which makes sense because you are turning the double bond on those two carbons into single bonds, right? And now you have four different substituents on each one of those carbons, okay? But again, in this reaction, those chiral centers are actually, when they're obtained, they're both in syn addition, right? Both hydrogens will either actually be pointing out towards you. Sorry, let me say that again. Well, yes, that's true too. Both the hydrogens will be pointing out towards you, and the substituents will be pointed in towards the paper, or the other way around, where the hydrogens will be pointed into the piece of paper, and then the substituents will be pointed out at you. Okay, so this is syn, and there's a reason for that, which we'll talk about in a second. So notice that when you try to do a hydrogenation reaction, it's actually incredibly slow, because the activation energy is super high, right? But if you bring in a catalyst, right, like PT, platinum, okay, the activation energy is like a fourth, right? And it goes through more steps, but that's okay. It's fast enough, and then you come down, right? But it's much easier to obtain, right? Because the activation energy is much lower than without the catalyst. So this is a close-up of platinum, right, and an alkene approaching platinum, with some hydrogen gas, bubbled in there, okay, in the reaction, and so the metal surface binds to the hydrogen gas, okay, and then the alkene, and so that explains why the hydrogen atoms are added in the same face of the alkene, or called syn addition, and it's because once the platinum attaches itself to the alkene, right, only one face of that alkene is pointed towards the platinum. Okay, and so since only one face is pointed towards the platinum, the hydrogens, right, come off and get attached. Not quite so simply. I'll show you a mechanism later, right? On the same side, right? It's not coming from the back side, because that side's not the side exposed to the platinum, okay? And then you get your hydrogenated product, okay? So syn addition of hydrogen gas is to a symmetrical alkene will not produce a pair of enantiomers, right? In fact, a mesocompound will be produced instead. And what that means is that you get this and this, but they're the same thing, because you flip one over, like if you flip it right there on that axis of rotation, right, it will be the same molecule, right? It will be the same molecule. So yeah, syn addition produces only one product, and it's a mesocompound. So practice this skill with Skill Builder 8.5. Predict the hydrogen gas products on Skill Builder 8.5. On Wiley Plus. There it goes. I was like, what is that thing called again? Okay, so let's keep trucking along here. So there are a couple type of catalysts that we can use to make this hydrogenation. I get add in the extra G for some reason. Hydrogenation reaction, right? And there's a heterogeneous catalyst, right? Like platinum or palladium, and that does not resolve in the reaction mixture. Okay. And then there's the homogeneous catalyst, which does dissolve in the reaction mixture and is accomplished by using ligands with the metal, right? And ligands are just, you don't know what this is yet, because this is really an inorganic thing. But ligands are molecules that will take position around a metal and donate electrons to those metals in a very geometric fashion, right? Very geometric fashion. So those are called ligands. So one of these ligands is actually called the Wilkinson catalyst, right? And it's a mother huge molecule. All of these are actually triphenylphosphines, right? That's a phosphorus with 3 phenols on it. Big, really big. Okay, so let's recall then that the creation of 1 or 2 chiral centers does result from a mixture in a mixture of enantiomers. And unless a mesocompound is produced, right? So here we have hydrogenation reaction happening with the Wilkinson catalyst, and we have 1 chiral center. Okay. And then we have creating 2 chiral centers with the Wilkinson catalyst. There, like we saw on the previous slide, right? Like we saw on the previous slide. And this is the mesocompound right here. So, if a chiral catalyst is used, it is possible to synthesize only 1 enantiomer of a major product. This can be accomplished by replacing the replacing the phosphine ligands on the Wilkinson catalyst with a chiral phosphine, right? Oh yeah, and this is the metal, by the way. And so instead of, for example, having the triphenylphosphine right here, which is the symmetrical phosphine, I feel really bad about this, but I can't remember what RH is. I'm gonna have to look that up. I don't do a lot of inorganic chemistry, so I can't remember what RH is. I'm gonna have to look it up. Rhodium. I was going to guess something completely different. But yeah, okay, so the metal in this case is rhodium. And the phosphines that are connected to the rhodium here, here, and here are triphenylphosphines, which is this right here, right? That's the symmetrical ligand, right? Each one of these is actually one of these. If you didn't already, oh, I'm sorry, my head's blocking the way. Let me move that out of the way. There we go. And literally, a triphenylphosphine is a phosphorus in the center with 3 benzene rings attached to it. So you can imagine how big that is, right? But the thing about it is that it is symmetrical, and you can use it to do the use it as the catalyst in your hydrogenation reaction, right? But if you want to do a synthesis in which only 1 enantiomer is the major product, right? Only 1 enantiomer is a major product, then you use a phosphine compound, right? That's chiral here. So this phosphine right here has a phosphorus in the middle, connected to a methyl group, a phenyl group, which is also a benzene, and then also connected to a propyl group, right? So propyl, methyl, and a benzene ring. So definitely not symmetrical. And using that, you can actually get a product that is only one enantiomer as its major product. Okay. So if a chiral catalyst is used, it is possible to synthesize only one enantiomer, right? So William S. Knowles developed a synthesis using L-DOPA as an asymmetric hydrogenation as a key step, right? So here the chiral catalyst was used on this molecule. Okay, this molecule. And this molecule is L-DOPA, and L-DOPA is actually a derivative of an amino acid. I'm not going to get too far into that. Let me bring myself back though. There we go. Right, and so he used a chiral catalyst, right, along with some hydrogen gas, and was able to get the S configuration only to come out, an enantiomer to come out of this reaction when he hydrogenated this double bond right here, right? And for that, he actually won the Nobel Prize in chemistry in 2001. Dang. So all you needed to do to get a Nobel Prize in chemistry, just one reaction? I would have worked harder in school had I known. So Roy, Ryoji Nayori. Let's just call him Nayori. Wow, my Asian ancestors would be rolling in their graves right now because I cannot speak. I cannot say this name. Anyway, he showed that the chiral ligand BNAP. See, his name messed me up for the rest of the lecture. BNAP, right? Also affords one enantiomer, right, with high selectivity. Notice here, this is BNAP. We saw this in a previous lecture, and we saw that it was chiral based on a asymmetric axis. Remember that from a little while back? I think it was in the stereochemistry lecture. Things come back to get you, right? Anyway, so he was able to hydrogenate this bond, this double bond right here, right, giving you this enantiomer in 95% excess, enantiomeric excess. Wow, right? So that was pretty efficient. He also won the Nobel Prize. Oh, both of them did. They won the Nobel Prize in chemistry in 2001, right? So I guess it was just an award for doing reactions that resulted in specific enantiomers. I guess that's impressive. So another reaction we can do with alkenes is halogenation, and it's exactly what it sounds like. You add two halogen atoms across a carbon-carbon double bond, right? So here we have our alkene. We have some chlorine gas, and you'll get 97% of chloride being added to the double bond, right? So this is actually very applicable to industry, and let me move my head out the way again for a second. There we go. You can start out with petroleum products where there's an alkene, right? And you do the halogenation reaction, and then what you can do now, after doing the halogenation reaction, is do an elimination of that, and you'll get vinyl chloride, right? And then after you get vinyl chloride, you can polymerize that reaction, or polymerize that. After you eliminate the chloride, one of the chlorines, you can do a polymerization reaction, right? And then it becomes polyvinyl chloride, right? PVC, which is literally in all our pipes, right? PVC pipe for plumbing. Okay, so all these reactions are very applicable to industry, especially the oil industry. Well, I say the oil industry because this is from petroleum, but then we go to plumbing because we're making polyvinyl chloride pipes, PVC pipes. Let me bring myself back. There we go. So halogenation is only practical with chlorine or bromine. Halogen with iodine gas and fluorine gas is too violent, right? Oh, so it's poor rather. Halogen halogenation with iodine gas is poor, and halogenation with fluorine gas is too violent. But here we go. This is the first time in this lecture we're going to have a halogenation, not halogenation, but an alkene addition, right? In this case, a halogenation that occurs anti-addition, right? And we'll see why that happens in a second. Let me just move my head out the way so you can see what's there, right? So you notice that these bromines were added to this double bond right here, and we get the anti-addition, right? Bromine coming out, and bromine going in, bromine coming out, and bromine going in. Okay. Let me bring myself back, and then go to the next slide. There we go. So this is why it does anti-addition, and I won't take myself away this time because the only thing right there is just a bromide leaving group. So I'll just write it again here for you. All right, bromide leaving group right there in that red circle. So bromine gas is nonpolar, right? Of course it is, because they're two of the same atom attached to each other, right? But in fact, it is polarizable. Okay, so when a nucleophile approaches, right, it induces a dipole in the bromine. So what then can happen is you can think of bromine gas, right, as a bromine atom that's connected to a super good, leaving group, because we already know bromide is a really good leaving group, right? So a nucleophile, of course, right, is negative, like no electrons, for example, from a lone pair, and as it approaches the bromine gas, we see that there's a temporary dipole being formed, right? And now there's a partial positive on this side of the bromine and a partial negative on that side of the bromine. Okay, so quite simply, what happens is that the double bond can do a nucleophilic attack on that partial positive bromine. Excuse me, and then the other bromine leaves as a bromide leaving group, and we get this guy right here. All right, and you guessed it. What can happen next? The bromide that left can come back and do a nucleophilic attack on that tertiary carbocation right there, right? To do the halogenation. I'm sure that's like the next slide. Oh, no, it's not the next slide. It's going to be on the next slide. So only anti-addition observed. So the mechanism is not consistent with a true carbocation intermediate. And what it means is that in a true carbocation intermediate reaction, right, which I actually said is, wow, I got that wrong, because it's so obvious, right, that like when you look here, it looks like it's so obvious that that's what could happen, right? Like a bromide can go and do a nucleophilic attack on that carbocation, but since it's an anti-addition, right, it's not consistent with a carbocation intermediate. Man, I would have gotten that wrong in the test, right? That's tricky. Make sure you remember that, okay? Make sure you remember that. The thing about it, right, is that if it was a carbocation intermediate, you would have a syn addition and you would have anti-addition, right? But that's not what you get, right? That's not what you get. What do you get, actually? Well, this is what you get, right? You get the formation of a bromonium ion intermediate, right? That is consistent with the anti-addition, right? So what can happen then is that the double bond comes up and forms this little triangle right here, right? It does the nucleophilic attack. It does, and then you lose the leaving group, right? And then some electrons from this bond, some electron density from the attached bromine, right, will come down here and fill in the gap there, right? And you get this thing called the bromonium ion, literally a triangle, right, with a bromine attached. Okay, with the bromine attached. The alkene functions as a nucleophile and attacks the molecular bromine, expelling the leaving group, the bromide leaving group, but then forms a bridged intermediate called the bromonium ion. And then now, since there's a bridged ion and the bromine is on this side, right, of the of the ring, okay, the only place for the bromide ion to do a nucleophilic attack is on the other side, and that's why it is a anti-addition. Okay, got to be careful about that. Okay, so here's the actual reaction mechanism, right? The formation of the bromonium ion intermediate is consistent with anti-addition, right? Bromide attacks the bromonium ion in an SN2 process and gives an anti-addition, right? SN2 because it's doing like a backside attack back here. It's the only place it can go. Let's go through this reaction one more time. I need to do it too, right? Where the double bond comes up, right? Attacks the bromine gas molecule, bromine molecule. Bromide leaves as a leaving group. Electron density comes back down from the bromine, goes back down to the carbon, right? The partially positive carbon right there. And so then you form the bromonium ion, bridged, right? Then the bromide, the leaving group, was a leaving group, now it's a nucleophile. And it's going to come over and do a backside attack. It has to do a backside attack because there's nowhere else for it to go, right? And then you get the bromine anti-addition, right? The bromine anti-addition plus enantiomer. Okay. So halogenation is stereospecific. The stereochemistry of the starting product of the alkene actually determines the stereochemistry of the products, right? So if you had a cis-2 butene and you did a halogenation reaction, right, you would get this product and this product, right? You get that product and that product where they're anti on both sides, right? They're anti on both products. Same thing here. No, sorry, not same thing here, but if you had a, well, same thing, yes, but if you had a trans 2-butene, right, and you did a halogenation reaction, you actually get a mesocompound. Still anti-addition, but a mesocompound. And if you rotate this molecule, you actually get that. So it's a mesocompound, right? Because you can actually rotate this bond that direction, right? Terrible arrow there. Let me just do that again. You can rotate this bond, right? And then the bromine at the bottom that was sticking into the paper will come up again and give you the same molecule again, right? So it's a mesocompound. Practice with conceptual checkpoint 8.24. Predict the product on Wiley Plus. Then we have the halohydrin formation, right? And halohydrin formation is really like a halogenation, except that you get a halide attached and you get a hydroxide attached, or an alcohol attached. Okay, so halohydrins formed when halogen is conducted in water. Water acts as a nucleophile that attacks the bromonium ion, right? And there are many more water molecules than there are bromide molecules, right? And that's why the bromonium ion is much more likely to be attacked by the water molecule than it's going to be attacked by the bromide ion. Because usually water is like your solvent, right? So just like before, we'll get the bromonium ion from the nucleophilic attack of the double bond to the bromine molecule. And then after that happens, we'll do a backside attack, SN2 style, with the water, and we get this product here, right? And eventually this this proton, one of these protons will get deprotonated, right? And we'll get the hydroxyl or the alcohol. Nope, and there it is. There's the actual reaction mechanism here. After water attacks, it is deprotonated to yield a neutral bromohydrin product, right? So let's go through this all again. Okay, we formed the bromonium ion from the nucleophilic attack of the double bond to the bromine molecule. Then we get the bridged bromonium ion. Water does its nucleophilic attack backside, like an SN2 style, right? And when it does that, this bond comes up here, restoring back some electron density to the bromine that's already attached. The hydroxyl, or the Water actually is on the other side now because of its backside attack. More water comes in, deprotonates, right, and then it restores electron density back to the positively charged oxygen, and that gives us our bromohydrogen product, right? Or it could be chlorohydrogen, okay, like there. Same thing, right? Same, not same thing, but same process, right? Same mechanism. Oops. There we go. So, so this is interesting too, right? Halohydrogen formation is regioselective, and so the halide will add to the less substituted carbon, while the OH will add to the more substituted carbon. Okay, that's very similar to the Makovnikov. That's what it is. That's very simple. That's very similar to the Makovnikov addition, right? But in fact, it's not Makovnikov. It's anti-Makovnikov because the halide is being added to the less substituted carbon, right? So bromine here in this reaction is being added to the side that has all the protons on it or the hydrogens on it, right? And then the hydroxide or the water is being added to the side with the CH3s, the methyl groups. So if you consider bromine, right, being the bromine being the substituted, right, the substituted the actual addition, the halide addition, right? It is the halide addition. Then this is very similar to the anti-Makovnikov, right, reaction. Okay, very similar to anti-Makovnikov. I froze for a second there because I was like thinking, is this the Zedzev and no, it's not, right? That's Zedzev and Hoffman product is the position of the double bond, right? Whether it's at the end or it's on the inside because of a bulky base and a slender base. We're going to get to that in a minute. It's hard to keep all these things straight sometimes when you're going through this so fast. Believe me, I know, and I feel your pain. I promise. Anyway, so yeah, this is super similar to the anti-Makovnikov addition. I'll just put anti-mark, right? Very similar to anti-mark. When the halide right here is the addition, right? And it's adding to the less substituted side. So here we go. Regioselectivity results from water attacking the more substituted carbon faster than it can attack the less substituted carbon. Okay. So here we can see that there are two methyl groups on the alkene here, right? On the alkene here. And so the water will do the nucleophilic attack here on this carbon. And mostly because that carbon, since it's like more substituted as well, it's got more partial positive character on it, right? So it's going to go there before it goes over here. And then it, kicks off the leaving group bromide, right? Bromine, but it's still attached on the other side. And then we get our normal water coming over, taking off the proton to reveal our alcohol, and we have our regioselective product, right, where the bromine will substitute on the side that is least substituted. Sorry, get added on the side that's least substituted, and the water will be added to the side that's most substituted. I just said that. The more substituted carbon has more cationic character. When I said it was more partially positive character, that's what I mean by that. That's why the water attacks here first rather than here, right? Because the more substitutions gives it a more partially positive character, as you can see here in the transition state. Okay. So we also have anti-dihydroxylation as well. In that reaction, we have the addition of two OHs across a double bond. Okay, two OHs. So here we can do ethylene, do a dihydroxy dihydroxylation, and then get ethylene glycol. Okay, anti-dihydroxylation of alkene is a two-step procedure, right? Where you actually end up with this cool little triangle here, bridge triangle epoxide, right? And you get the transdiol. Okay, you get the transdiol. And notice here it is a transdiol because you have the hydroxyls or the alcohols coming out at you and going into the paper. Okay. So let's talk about the mechanism for that reaction. Okay. First thing to do is to actually create the epoxide. Okay. And what's being used here as the reactant or the reagent is a peroxy acid. All right. Specifically, the peroxy acid is peroxyacetic acid. Notice that it looks a lot like acetic acid, right? Except that there's an extra OH or extra H. There's an extra O right there, and that's why it's called peroxyacetic acid, right? So I don't know if you notice this, but whenever there's an extra O somewhere, it's called a peroxy, right? It means extra O. Okay, per means extra, and then O, oxy, right? For example, hydrogen peroxide is this. It has two O's in there instead of one O like water does. That's why it's called peroxide, right? Hydrogen peroxide. And then peroxyacetic acid has an extra O right there, right? And that's why it's called peroxyacetic acid and not called just acetic acid. Because if it didn't have the extra O, it'd just be normal old acetic acid. But we have to use a peroxyacetic acid for this mechanism, okay? And well, it doesn't have to be peroxyacetic acid. It just has to be some kind of peroxy acid, because you can see here we have a chloroperoxybenzoic acid, and that works just as well. So again, double bond comes over here. This is a little complicated, so follow me here, right? Okay. The double bond does the nucleophilic attack on the oxygen, okay? And then the oxygen releases its double bond to this oxygen, right? When it does that, that double bond comes down, right, and then releases the double bond from the carbonyl oxygen and carbon to pull off, to deprotonate itself, right? And once it deprotonates itself, those electrons go over and fill in electron density for that positive carbocation, or that partially positive carbon right there, right? That results from the loss of the double bond, okay? So when that happens, we get our transition state, and our transition state yields us our epoxide, right? Our epoxide. And in this case, it also yields us our acetic acid. So the peroxy acid just lost one of its oxygens, right, to the epoxide, and now it's a regular old acetic acid. And that's how we form an epoxide, okay? So let's just go through these steps one more time. The double bond comes over and does a nucleophilic attack on the oxygen, right? The one that's closest to the hydrogen. And then when it does that, the bond between the peroxides, right, comes down and forms a double bond between the carbon and the oxygen, right? That effectively releases that oxygen, the peroxy oxygen, right, to go join the alkene as an epoxide. But the reaction's not done yet, because once you form that double bond there between the carbon and the oxygen, the double bond that was originally there from the carbonyl oxygen and carbon has to release. And when it releases, it goes and deprotonates the peroxide, right? The peroxide oxygen that had an extra proton on it, right? And then the electrons from that bond flow over to fill in an electron density gap right there from the loss of the double bond of the original alkene. Okay, and then you get your acetic acid left over with your epoxide. Then next thing you have to do, right, you have to react the, you have to react the epoxide with water and an acid catalyst to form the antidiol. Okay, so water comes over, okay. It's water and acid, so that's why we have the hydronium ion right here. Okay, and then so the epoxide can come over and deprotonate the hydronium ion, leaving you with just water. Okay, and now we have an oxygen with 3 bonds to it, so it's positive. Now actual water can come over and do a nucleophilic attack, right, just the same way it did in the bromonium ion, right? And then that bond gets released, and you get an OH left over on that side. The water, since it did this in an SN2 fashion, does a backside attack. You get a water added anti to the original hydroxide from the epoxide. And then water can come over and deprotonate the water, right? Giving you a hydroxide or a hydroxyl or an alcohol, whatever you want to call it, right? And that gives us our anti-addition of the alcohols, right? On both sides of the cyclopentene, okay? Cyclopentene. And remember, just remember, both the epoxide reaction mechanism and the bromonium ion mechanism, right? You know, when the nucleophile gets attacked by the water, excuse me, by the water, it's an SN2 style attack, right? And so that's why it's going to be on the backside, and it's going to have anti-addition. Excuse me. Now to something that I literally spoke of seconds ago. Note the similarities between these three key intermediates. So we just talked about the protonated epoxide right here, right? And that's where we have the oxygen as a bridging atom between the two carbons that used to bear the double bond, right? The pi bond. And then we have the bromonium ion, which was the reaction before that, right? Here we also had a bridging atom of bromine, all right? A bridging atom of bromine. And then if you reach back to yesterday's lecture, we had the mercuronium ion, right? Mercuronium ion. And that was a part of the oxymercuration reaction that we were talking about yesterday, where we can prevent the carbocation from rearranging because of the mercuric acetate ion here acting as a bridge, right? Bridging atom between the two carbons, right? Before the addition reaction, okay? So notice that they all have positive formal charges, but the more important thing to notice is that all three of these that have these bridging atoms as a part of their intermediates, right? They all yield products that have anti-positioning of their substituents, right? And remember, the reason why is because the nucleophile has to attack from the other side of the leaving group, just like it does in an SN2 reaction where it does a backside attack, because that's the only place it can go, right? Remember that I'm just going to use some, I don't know why I wrote BR there. There's already BR there. You know, because I'm trying to draw a nucleophile. There we go. Right? We have a nucleophile. It's got to attack from the backside over there, right? Or the backside over here. Or the underside in this case, right? Or the underside over here. And that's why these reactions that have these intermediates in alkene addition reactions always yield anti-products, right? So remember that. Practice of Skill Builder 8.7, predict the products on Wiley Plus. Okay, so now we're going to look at syn dehydroxylation reactions, okay? They add OHs across the double bond in a concerted syn fashion on the same side, right? And here, our oxygens are coming from the osmium tetraoxide. I think that's what it's called. Yeah, it's osmium tetroxide reagent. Okay, and again, we can do a little nucleophilic attack here with the double bond to the oxygen. We lose that bond there, and then this kicks up over here, right, to fill in that electron density. And again, we have a bridging moiety, right? And this time, though, the epoxide, right, is sort of on both sides, sort of, because, you know, it's not a carbon over here, right? But now we have oxygens on both sides. But the interesting thing, though, to note is that they are syn added to the cyclohexane, right? They're syn added. They're on the same side. In contrast to the anti-addition, right? Or the anti-syn the dihydroxylation, right? So this molecule here is the acyclic osmate ester, right? Osmate ester. So not the epoxide, but an osmate ester. That's that part right there. Okay. And then once you have it as the acyclic osmate ester, you can treat it with sodium sulfite in some water, or sodium bisulfite in some water, and we'll lose the osmium moiety, right? The osmium portion, and we'll get the hydroxylation in a syn fashion, right? Concerted syn fashion. So it turns out, though, that osmium tetroxide is expensive and toxic, right? So NMO, or alkyl peroxide, is used as a co-oxidant, so only a catalytic amount of osmium tetroxide is necessary. So catalytic amount means very little, right? And the reason why you can do that is because whenever you have in a catalyst, right, after reaction is done, the catalyst returns to its normal state again, right? It becomes what it originally was, right? It doesn't get used up. All right, so this is the structure for NMO, and I do not remember what NMO stands for, right? And then we have here the alkyl peroxide, right? In the presence of the catalytic amounts of osmium tetroxide, and you get 60 to 90% of the syn dihydroxylated cyclohexane. You can also use potassium permanganate in this kind of reaction too to get syn addition, right, of the hydroxylation, right, or dihydroxylation, right, but only under milder conditions, cold temperatures, right. So the synthetic utility of using potassium permanganate, though, is limited because it reacts with many other functional groups as well, right? But it is possible to do a dihydroxylation syn style, right, with an alkene like this cyclohexene, right, and come up with the dihydroxylated syn style 85% worth after treating it with some sodium hydroxide. So practice this conceptual checkpoint 8.31. Predict the product on Wiley Plus. The next reaction we're going to talk about is the oxidative cleavage, right? Carbon-carbon double bonds are also reactive towards oxidative cleavage. Excuse me. Ozonolysis is one such process where we use ozone, right? We use ozone. Ozone is oxygen, 3 of them together, right? With some DMS, and we can literally break this molecule in half, right? Through oxidative cleavage. You literally are cleaving the bond, right, where the double bond is, by oxidation using ozonolysis, right? So ozone actually exists in a couple different hybrid forms, right? You've got this hybrid contributor here, right? And then that hybrid contributor over there, right? It's all resonating back and forth, or somewhere in between. So how do we do an oxidative cleavage using ozone? Well, we can start out with an alkene, of course, right? And the pi bond from the alkene can do a nucleophilic attack on that oxygen on the far side there. That releases that pi bond so that the electron density goes to the center oxygen. And then the electrons from the last oxygen will come over and fill in electron density there at the opposite carbon. Okay? What that produces is the initial ozonide intermediate, right? The initial one, also known as the molozonide. Okay. Well, after that happens, right, the pi bond from this carbonyl can come over and do a nucleophilic attack on that carbonyl carbon there, releasing that pi bond from the oxygen, right, from the carbon to the oxygen, right. leaving this electron density from this last oxygen to come back down and fill in the little electron gap, right, that was left when the pi bond was released, right? And once that occurs, our intermediate is now an ozonide. Okay, it's the ozonide. Notice the difference between this ozonide here with all three oxygens on the same side, and then this ozonide here with one oxygen on one side and two oxygens on the other side. Okay, it even looks more stable. You can even take then a mild reducing agent like dimethyl sulfide, right, DMS, or zinc/water, and do some reducing, and you can break that into two acetones, right? Two acetones. So literally then what happened, if you notice that from this alkene right here, right, the bond got broken right down the middle, okay? And then right where the bond broke and down the middle, we got two ketones out of it, right? Just put two oxygens in the middle of that double bond right there, right, of the alkene, and you have the products for an oxidative cleavage. The practice on skill builder 8.8 predict the products on Y plus. So we have another oxidative cleavage here, except we already have the product, and it's asking us to form to give us the reagent, right, whatever the molecule was, the bicyclic molecule was, that created this, right, The first thing to note, though, is that, we need to know how many carbons there were, right, and we can already see that there's 1, 2, 3, 4, 5, 6, right, 4, 5, 6, so that means that we already have a cyclohexane. It looks like the double bond was between this carbon here, and you can't see where I'm drawing, but this carbon over here and this carbon over here, right? So that's where the double bond will be on the cyclohexane, okay? Or I guess it's called cyclohexene now, okay? Then we have double bonds down here and here, right? How many carbons are there? 1, 2, 3, 4, 5. Right, and we have oxygens down here, right? Ketones down here. So these used to be connected to each other. Okay, those used to be connected to each other. So we know then we have a cyclopentane. And where would that double bond be? Right? Looks like it starts over here, right? So at the bottom of that that hexane, right, the cyclohexane, right where it meets right here, that's where the double bond was, because that's where the ketones ended up, right? So that's where the double bond would be for the cyclohexapentene part. Okay, cyclopentene part. Oh, and of course the next slide has the answer, as I always forget or don't realize, but that is what we got on the previous slide. Good job, team. Good job. So now let's review how to predict the products of addition reactions, right? The first thing you need to do is analyze the reagents that are used so you can determine what groups will be added across the carbon-carbon double bond, right? So, if it's a bromine being added or a water or so forth, right? The next thing to do is determine whether or not it's going to be Markovnikov or anti-Markovnikov, right? Whether it's going to be just, quick review, if it's going to be adding the new substituent, right, onto the side that's most substituted or the side that's least substituted, right? And that's what we're talking about when we're talking about Markovnikov or anti-Markovnikov. Then you've got to determine the stereospecificity, right? And in determining the stereospecificity, right, we're talking about whether or not the substituents added are going to be syn to each other or anti to each other. And remember, just like we talked about in the last slide, if you're going through that intermediate where you have a bridging atom, like an oxygen, a bromine, or even a mercury, you're always going to get an anti-addition, right? So the more you familiarize yourself with these mechanisms and the reagents that are in this chapter, chapter 8, and even the previous chapter, chapter 7 too, the easier it will be for you to predict those products, right? So practice with Skill Builder 8.9 on Wiley Plus. Predict the products, okay? So how do we plan a one-step synthesis? Well, first thing you're going to do is you got to assess the reactants and the products to see what changes need to be made, right? So when doing that, it could be any combination of things, where it could be an addition reaction, right? Everything that we've been talking about for the last chapter, today and yesterday, right? It could be a substitution reaction, just like we were talking about last week, right? A substitution reaction, where we have a nucleophile come in, right, and does a nucleophilic attack on that carbon right there, right, and then the leaving group leaves, right, and then you're substituted with the nucleophile, or it could be an elimination reaction, right, also from last week, okay, where we have a base come in. Let me draw a proton there, or 3 since I'm already on it, and a base can come in like ethoxide, like so. Pull off that proton, this thing comes down like this, right, and then the leaving group leaves, right? So it could be any one of those 3 types of reactions, or a combination of them all together, right, to synthesize the molecule that you want to synthesize, right? So for example, for this particular reaction, right, give the reagents and conditions for the following, right? We can see here that we're getting an OH, right? So we already know that's an addition reaction, okay? Which means we have to add an H and an O, right? An H and an O. And we need to make sure it's Markovnikov regional chemistry, right? Regiochemistry, okay? Gotta make sure it's Markovnikov regiochemistry. So what do? How do we get that? Well, first thing is we know that we can do water to add the OH, and we can have some protons from sulfuric acid, right? And that will give us the Markovnikov regiochemistry addition of the alcohol. Okay? Okay? Practice with additional examples in Skill Builder 8.1. Propose a synthesis. Okay? Or, how do you change the position of a halogen? Okay? The following transformation cannot be done with a single reaction. We want to move this bromine right here over here. So that can actually be accomplished with a 2-step sequence, 2-reaction sequence, right? First thing we do is we do an elimination of this bromine. Okay, we do an elimination of this bromine. And then we can do an addition of this bromine across double bond, right? So, how do we accomplish that? Well, first thing to do is to do the elimination. So let's put in a strong base, right? And we want it to be a ZZF product, right? We want most of it to be ZZF product, right? So that's why we're going to use a non-bulky base, or I like to call it a slender base, right? So that the base goes and attacks the side that has the base will the base will extract the proton, right, from the side that has the has the most substitution. Okay. And so, quite simply, we can go over here and pull off the proton that was sitting right here. Right? And then this double bond goes down, this bond goes down here, forming a double bond, and the bromine leaves. Okay? Then, we can decide the reagents that we need to add on a hydrogen and a bromine, right? Or also known as a hydro halogenation, which was the very first reaction we did in the addition reactions of alkene chapter at the very beginning of yesterday, right? So we already did this part right here where we did the elimination of the bromine using the sodium methoxide, right? And then we'll do addition now to get this, okay? Easy way to do that, which is what I just said, the hydrohalogenation. Have our HBr right there. Okay, have the HBr right there. And then the bond comes over. The pi bond comes over and does a proton transfer, right? So then you're left with the carbocation right here. And the proton gets added on over here, right? And then the bromine, which is a bromide now, has a nucleophilic attack on that tertiary carbocation, and it gives you that, which you can't see because my head's in the way. But there we go, that. And that's how you get from a bromine being over here, right, to a bromine being over here. Let me bring myself back. There we go. Or, how do you make it so that the OH that was here gets moved down to the end of that carbon right there? Right? How do we do that? Okay. Well, this isn't a simple, it's not a simple substitution or addition or elimination. So we have to do it in two processes, right? First thing we do is we'll do an elimination. Notice that we have an elimination using getting a Hoffman product here, right? The Hoffman product is always when you have a double bond at the end, right? Not somewhere in the middle, but in the end, right? So we have a Hoffman product. So there's got to be some kind of bulky base here, right? Like a tert butoxide. TOBU. Is that how they do it? Is that the abbreviation for tert butoxide? We'll see. And then after that, we can do an addition, right? A hydration using H and OH, right? Or do hydration, right? So we can get an H and an OH across the double bond, which you can't see because I have blocked it with my head once again. There we go, right? Let's see what base they chose. I don't know. Okay, so here we're doing an elimination, and it must be done to give a Hoffman alkene, right? So the first thing we have to do is, I forgot this step, so this is important, and so you should remember this step too, right? OH is not a good leaving group, right? But turns out that the tosylate is, which is this guy right here, right? So you add in the tosylate and the pyridine, and it replaces the OH with the OTS, okay? And then, like I was saying before, we do the elimination product, we do the elimination reaction using a tert butoxide, right? This is potassium tert butoxide. That gives us our Hoffman product, where the double bond is at the end, right? And let me just show you, there we go, double bond is at the end, okay? So then the next thing after that is we can do a hydration reaction. Okay, so let me bring myself back. There we go. And in this case, we're going to be using, we want to do an addition reaction that will give anti-Markovnikov addition, right? Excuse me, of H and O. And if you recall, back in the first lecture of this chapter, right? We did that by using the hydroboration oxidation reaction, which is this right here. Right? Hydroboration oxidation reaction. Okay? That uses the boron trihydride, like I always call it, but most people call it borane. THF, tetrahydrofuran, hydrogen peroxide, and sodium hydroxide. And that will give us our anti-Markovnikov, right? Addition of the OH and the H, right? From the Hoffman product. Okay? So practice with Skill Builder 8.11, changing the position of a group, right, on the Wiley Plus. How about changing the position of a double bond? Okay. Again, this has got to be done in 2 steps, 2 processes. We can do an addition reaction first, right? An anti-Markovnikov addition of H and Br. Okay. And then we can do an elimination to give a Hoppen product. By now, you should know that if you want a Hoppen product, what do you have to use? A bulky base, like terbutoxide, right? So next. So to change the position of the pi bond, right, we're going to have to do an anti-Markovnikov addition of the hydrogen and the bromine, right? And if you recall back from the previous reaction, previous lecture, all you had to really do was have your reaction take place in the presence of some peroxide. Even trace amounts was enough to get an anti-Markovnikov addition of the bromine, as you can see here. Okay, and then, like I said in the previous slide, if you want to have a Hoffman product, which is a double bond at the end, right, towards the end, all you have to do is make sure you have a bulky base, like terbutoxide. Okay. So, practice with skill builder 8.12, changing the position of a pi bond. So, let's just review now all of the different kinds of alkene reactions that you can do. And we'll go around in this little circle and put it all together. Okay? So, the very first reaction that we have here, coming from this alkene, right there, right? Coming from that alkene right there, right? The first one we have here, number 1, and there's 10 of them, so I'm pretty sure there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there's 10. So number 1 here is the hydrohalogenation. Okay, that's the hydrohalogenation reaction. That's number 1. And the way we accomplish that from this alkene is by just exposing it to a halide, right? A hydrogen halide, like HBr, or a HCl, right? Hydrogen chloride gas, right? And that was hydrohalogenation. And that will put the X here, could be a chlorine, could be a bromine, right? Where the X is on the product, up here, right? The second one we have here, I have to, my hand is, I need to, turn it so I can write right here. The second here, number 2, is the anti-Markovnikov halogenation. Right? But this time it's anti-Markovnikov. Anti-Markovnikov, right? Just so we don't get confused, I'll put Markovnikov addition here. Normal Markovnikov. Okay, but this one's the anti. And remember, we just did it in the last slide. How do we achieve an anti-Markovnikov addition of the bromine in this case? Right, from this alkene, we just use the hydrogen bromide, or it could be anything, right? Hydrogen bromide could be hydrogen chloride, right? But here it has bromine. But all you have to do is have it in the presence of also a peroxide, some kind of peroxide. Okay. Okay, so over here, the next one is number 3, and this is the acid catalyzed hydration. That's the acid catalyzed hydration, right? And how do we accomplish that? How do we accomplish that from this alkene? Quite simply, we add acid and water. And when we add acid and water, what do we have? We have the hydronium ion. And that's all you really have to do there. Okay, that's all you have to do there. Right? But the only problem with that is you'll get like, you won't get like all of the same product, right? You'll have a mixture of products because you might get like a rearrangement of the carbocation, right, to a more stable carbocation, and you won't get the all of the product that you want, right? So that brings us to reaction number 4, which will give us a non-rearranged hydration. Okay. And that was the oxymercuration, which I have no idea if I'm going to spell this right. Mercuration dash demercuration reaction. Okay. And the way we accomplished that was by having first some mercury, I can't remember I remember what the formula is, but I can't remember the name. OAC, right? 2. And then we also need to add in some water, of course. And then we also need to have the sodium borohydride to do the reduction afterwards. Sodium borohydride. Okay, sodium borohydride. Okay. Somebody in the comments below tell me what the AOC stands for. I always forget what that one stands for some reason. Then, what do we have next here? We have this right here. We're going to go from this alkene to this syn addition here, right, of the OH. Okay, and we can do this by reaction number 5, which is hydroboration oxidation. Okay. In hydroboration oxidation, we have the boron trihydride. And then we also have the THF, the tetrahydrofuran, right? And then we also have to do the oxidation part, right? And we're going to accomplish that by adding in some hydrogen peroxide, H2O2, along with sodium hydroxide. Okay. Next reaction that we can get using this alkene is the hydrogenation reaction. That's number 6. Hydrogenation. Okay. And the only thing we need for hydrogenation is H2 and a platinum catalyst, right? This one's pretty easy, number 7, because literally you see bromines there coming off of the alkene now, addition of the bromines. So this is bromination. And the only thing we need to have for bromination is Br2, bromine gas. Okay? And then number 7 here, this reaction, where we have the hydration. We have the halogenation and we have a hydrogen, right, formation. This is number. I'm sorry, I miscounted here. I just realized I'm gonna end up with 11. So let me see what I did here. That is. Oh, here we go. I counted oxymercuration as a separate reaction, but both oxymercuration and acid catalyzed hydration do the same thing. The only difference is that oxymercuration, demercuration will give you the unrearranged carbocation, right? So you'll get it where you want it to go, right? So that's actually a part of 3. So we'll call that 3A, and we'll call this one 3B, okay? 3A and then 3B. So that makes that reaction number 4. That reaction is number 5. That reaction then is number 6. Okay, number 6. My apologies there. I was counting and I was like, I'm going to end up with 11. That doesn't make any sense. I thought there were only 10 reactions. Don't want to give you 11 reactions when there's not 11 reactions. Excuse me. Okay, so number 7 here then, where we get the halogenation and the hydrogen formation, right? It's actually, literally that's what it's called. Number 7 is the halohydrin, right? The halohydrin formation reaction. Right, and I'm blocking it with my head once again, so let me move out of the way. There we go. And to do a halohydrin formation, right, all you need is Br2 and some water. Right, and remember the reason why that happens is because the water will do the attacking much more often than you would have bromine, because there's more water there, because the water is the solvent. Okay. So reaction number 8 here is the anti-dihydroxylation. 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 Okay. And to do a dihydroxylation, anti-dihydroxylation, we need this reagent here first, ROCO3H, and then we need some acid, right, which we'll label as H3O+. And again, this reagent here, I cannot remember what the name of it is, so down in the comments below, please remind me if you are watching this on YouTube. And then we have our syn addition right here, but so that's reaction 9, and that's the syn anti-hydroxylation. And in the syn anti-hydroxylation, we can go about that a couple of ways. We can use potassium permanganate, which isn't as common, right? Because potassium permanganate can actually react with a lot of different things, so we don't use it that much. But we have potassium permanganate, right, along with some sodium hydroxide and some coldness, some cold temperature, right? But the easier way to do this reaction is using the osmium tetroxide. I can't believe I remember osmium tetroxide, but I can't remember the name of the RCO3F. Yeah, whatever. I don't even remember what the formula is. So first we do the osmium tetroxide. Okay. And then we'll do the sodium sulfate, bisulfate. Sorry, that's sulfite, actually, I'm sorry. It's bi because it has it's bisulfite because it has the hydrogen in front of it, right? SO3, sulfite because it's SO3. Okay. And then we're also going to add to it some water. And that's really hard to see. I'm going to move that out here. Move that out here for you so you can see it better. Yep, those are the reactants there, okay? Number 2. Okay. Number 2. And then last but not least, we have broken open a ring here using ozonolysis, which is reaction number 10. Ozonolysis. And if you recall, well, I recall that doesn't look like an S, but let me try that again. There we go. That's good enough. And if you recall, the way we do an ozonolysis is by using ozone, right? And some D So I'm going to tell you now that these are the 10 reactions that you need to know, right? The 10 type of reactions, 10 types, the 10 types of reactions, 10 type of reactions. I'm not good at English. These are the 10 types of reactions that you need to know for the additions chapter, okay? I will test you on these 10 reactions. So what you need to know is how to recognize which reaction is happening, right? Or know what reagents are there. And you don't even have to really know the name of the reagent. Like I forget the name of the reagents, but I still remember what the formula is, right? All right. So you need to know what the reagents are that are required to do these reactions, these 10 reactions. You need to know what the products are going to be, right? You need to know their regiochemistry, right? And their stereoselectivity or stereospecificity, right? But for this chapter, chapter 8, you need to know these 10 reactions, frontwards and backwards, and be able to apply them to all kinds of different molecules. Okay? So that actually ends our lecture for today. I'm going to bring myself back. Due tomorrow by 7:59 a.m. Will be your addition reactions of alkenes assignment, and then also quiz 9 is due tomorrow by 7:59 a.m. Remember that you have your exam 4, your last exam before the final exam on Friday. That's June 25th, and then by the end of the day tomorrow, don't forget that you have a lab that's due. That is the iris spectroscopy lab, and there will be a pre-lab lecture recorded, posted for you. And soon, very soon, I promise there will also be an exam 3, exam 3 solutions video posted for you. All right. Good luck learning those reactions, and I'll see you in the next lecture.